solid to a liquid or gas or go back again just by changing its pressure and or temperature. But that's not immediately obvious to us in a world where the temperature and pressure don't change much at all. In the narrow band of temperature and pressure we live in, most of the things we encounter are either solid, liquid, or gas and stay that way. Water is the obvious exception. When I said I saw snow, water, and ice together in the same place at the same time on a beach in winter, I was cheating, ever so slightly. The snow on the beach is at a slightly low temperature than the water in the ocean, while the water vapor in the sky is at a much lower pressure. So, in fact, the three states of water coexist in my photo because they are in quite different conditions on land, ocean, and sky. Compared to water, other substances need much more extreme changes of temperature or pressure to change their state. If you want to change something like a block of iron from a solid into a liquid, you are looking at a heating to temperatures of about 1500 degrees Celsius. On the other hand, to change an everyday gas such as nitrogen into a liquid, you would need to cool it down below about minus 200 degrees Celsius. Suppose you fill your balloon with steam to start with. Cool it down for a while and you would get a balloon with a bit of water inside. Then a balloon frozen with ice. If you keep on cooling, you take more and more energy from the molecules inside. Even the atoms or molecules in a solid do move about a little bit, but they are like people running on the spot. They oscillate more or less around a fixed position. The more you cool a solid, the less the atoms or molecules move. Could you reach a point where the atoms or molecules stopped moving altogether? In theory, yes. If you figure out the numbers, you would need to cool down to minus 273.15 degrees Celsius, which scientists describe as the lowest theoretically possible temperature or absolute zero. In practice, it looks impossible we could ever cool things down this much, though researchers have got pretty close. The modern Kelvin scale numbers up from 0 Kelvin in temperature units, the same size as degrees Celsius. So the freezing point of water becomes 273 Kelvin and the boiling point of water is 373 Kelvin. Temperatures on the Kelvin scale are written without a degree sign. If you heat a liquid, sooner or later you get a gas. But what happens if you keep heating? Eventually, you produce a fourth state of matter called a plasma, in which the gas molecules not only separate from one another but break apart into their subatomic components, electrons and ions. Plasmas are used in plasma TVs, among other things. When a liquid comes into contact with a surface, both cohesive and adhesive forces will act on it. These forces govern the shape which the liquid takes on. Due to the effects of adhesive forces, liquids on a surface can spread out to form a thin, relatively uniform film over the surface, a process known as wetting. Alternatively, in the presence of strong cohesive forces, the liquid can divide into a number of small, roughly spherical beads which stand on the surface, maintaining minimal contact with the surface. The molecules of a liquid, like those of a solid, are quite close together. However, while molecules in a solid are held in a fixed positions by intermolecular forces, molecules in a liquid have too much thermal energy to be bound by these forces and move about freely within the liquid, although they cannot escape the liquid easily. Although the molecules of a liquid have greater cohesion than those of a gas, it is not sufficient to prevent some of those at the free surface of the liquid from bounding off. On the other hand, the cohesive forces between the molecules at the surface of a mass of liquid and those within cause the free surface to act somewhat like a stretched elastic membrane. It tends to draw inward toward the center of the liquid mass to draw the liquid into the shape of a sphere, thus exhibiting the phenomenon known as surface tension. A liquid is said to wet a solid substance when the attractive force between the molecules of the liquid and those of the solid is great enough to hold the liquid's molecules at the solid surface. For example, water wets glass since its molecules cling to glass surfaces, whereas mercury does not since the adhesive force between its molecules and those of glass is not strong enough to hold them together. Capillarity is an example of surface tension and adhesion acting at the same time. Surface tension is caused by the attraction between liquid molecules along the surface of the liquid. Most of the molecules in a liquid have several neighboring molecules that they interact with, but the molecules along the surface have no neighboring molecules above them, which increases the strength of surface molecules with each other. Surface tension can cause the surface of a liquid in a small container to be rounded. It can also support materials that are denser than the liquid as a whole. For example, a needle or paper clip can float on the surface of a glass of water, but if the surface tension is broken, they will both sink to the bottom. Surface tension of soap solution is less. It can spread over large areas and wash clothes more effectively since the dirt particles stick to the soap molecules. In soldering, addition of flux reduces the surface tension of molten tin, hence it spreads. Antiseptics like Dettol have low surface tension so that they spread faster. Surface tension prevents water from passing through the pores of an umbrella. A duck is able to float on water as its feathers secrete oil that lowers the surface tension of water. With this, we have come to the end of this chapter. Go through the video again and familiarize yourself with the concepts you find difficult. And also check out the games and quizzes we have in store for you. Till the next session, goodbye.